All right. Hello, everybody. I've got a project here I've been really excited to tell you about. I spent the last 5 months developing my own audio plugin. It's right here. It's called Crunchberries. It simulates the iconic MESA Boogie Mark IIC Plus preamplifier. So why would I make this plugin when the modeling market is so heavily saturated right now? What's so different about this plugin compared to all those other modeling plugins out there to make this 5-month time investment worthwhile? Well, if the screen hasn't given it away yet, you could kind of tell that this plugin simulates the preamp by directly simulating the circuit itself. Now, I don't mean that's some sort of like approximation modeling or trickery like wave shaping. And I definitely don't mean there's any sort of neural network engine or AI in here of any sort. I mean it literally simulates the circuit itself. That includes every resistor, every capacitor, inductor, potentiometer, and of course, the 12AX7 tube stages. All right, so why would you believe me? I could just draw a schematic on here and do whatever I want, right? That doesn't mean it's simulating. I could be tricking you entirely here and running it through a real amp or something. To prove it, let's take a look here. So we can zoom in with this schematic layout, and you can see here all of the values for the resistors and capacitors are all shown here. If you're overwhelmed, don't worry, you don't need to play with any of this, but I'm just going to demonstrate it just to kind of let you know what's going on here. So if I hit a chord and I start fiddling with some of these resistor values, can't fake that. Right? Regardless, we can kind of tweak some more significant things. So let's turn off the treble shift, for instance. So you can see that little switch just opened up. This is literally simulating the switches. But now we have kind of a different sound, and we have this resistor is now active, since it's not being shorted anymore around that switch, that closed switch. If I go ahead and play another chord, and I play with this resistor value, perhaps this will be clearer if I turn the lead channel off. The higher the resistance, the less you hear coming out. It's getting louder. But let's just double click and return it to its original value. Or we can just bypass it entirely with the treble switch. We could also engage the bright channel, or the bright mode rather. So all that does is loop in this little capacitor here, the bright cap, which we can tune. That's no longer a bright cap. But if we pull it down, maybe around here, we get kind of a different sound. So it's very sensitive to these parameters here. Well, some of them contribute more than others. I like to turn that off because it kind of removes a little bit of the low end. Speaking of the low end, we can flip this bass shift switch and get a lot more. You can kind of see the impact that has. Just brings in the low end because there's no longer a resistor tied to this capacitor that's filtering it out. And to that point, we can play with that resistor as well. So the lower it goes, the more bass I get out of it. And that makes sense. That's consistent with closing the switch, which effectively is no resistance. And on the opposite end, if I go higher, I get less bass. If I drop this all the way down, like 1 ohm. The bass comes back. If I double click, it comes back to 15K. I could just as easily play with these capacitor values. See, there you go. If I boost this one up, I get no signal. You can hardly even hear it. There you go. We are definitely simulating this circuit in real time. There's a ton of parameters here, of course. So we can take a look at, I've got 3 different models of a 12AX7 tube, basically categorized into a brand new tube, a slightly used tube, and then a very old tube. So if we take a look at the new tube, and we switch to a used tube, you're not going to hear that much of a difference, but it does reduce the output and reduces the gain a little bit. Versus an old tube has a significant impact there. You can hear this more with the lead mode engaged. And especially obvious if we switch to the output stage. This is over here in the end. Because that directly affects how much output is coming out of the final tube, and that drives kind of the amplitude of the signal at the very end of the stage. So we'll switch that back to used. The other cool thing that you probably noticed by now is this oscilloscope, and it is tied to whatever the yellow wire is selected in the schematic. I can shift click and deselect that, and I can show you something else entirely. We can look at the signal as it goes through the preamplifier at different stages. This is basically the rhythm sound without the lead mode engaged. So if we switch off those little switches, we can see we're still on the clean sound. And you can see that on the oscilloscope. So if I turn on the lead mode, that's not affected. What you're seeing is always that same note. Right? And then we can look at after some of these mixer components. Should be the same, but it's a significantly reduced signal level. So we kind of have to zoom in here a little bit. Right. The 2C Plus is famous for doing this additive gain stage. So the lead mode, all the overdrive, is right here in these 2 tube stages and these supporting components. So this massively amplifies the signal to the point of clipping, obviously beyond clipping, in these 2 triode stages. So if we enable the lead mode, you'll see most of the distortion coming from this section. And yeah, there you go. It's a big square wave. Let me zoom out a little bit. You can see the bottom. And this is kind of what tubes do. They basically amplify the signal until it gets to a clipping point, and they sort of asymmetrically clip. Like you could tell on the top of the waveform is very square, and on the bottom it's more rounded. So this produces more odd harmonics than even harmonics. But of course, there's more after that. There's still these other 2 tube stages, which contribute to the final sound as well. And in the original circuit, there was an effects loop here. I've sort of hacked the circuit and removed the effects loop because it's not going to work like that in this situation. So instead, we're always just sampling the output at the end of the circuit. And this is basically the output of the preamp, but this is the graphic equalizer tacked onto the end of it. So if we look at the signal before versus after, we can tell kind of what the EQ is doing. But if we look at the very final output, turn the EQ off, you can see what the EQ is doing to the signal. preamp is basically turning this thing into almost a square wave. You can see there, squarey, kind of rounded, as the harmonics start to disappear. If we turn the EQ on, very different story. Those initial transient high peaks on every waveform are the high end. And then similarly, if I toggle this deep mode, we can see what effect that has on the waveform. There's a lot more amplitude overall with the low end engaged. How does this plugin stack up to a real preamp? Well, let's find out. What I've got going on here is I've got the preamp into the effects return of my Mark V. And the Mark V speaker output is connected to the Torpedo Live, which has a cabinet IR on it. And that's kind of what you're hearing coming back through the system here. So at any point in time, I can use the foot switch on the Mark V to enable or disable the effects loop. And I also have the guitar broad signal going into the front of the amp. So I've got it split going into my plugin and going into the amp, and I've matched the gains on those, so there's no real significant difference there. And what we're basically comparing is this preamp circuit plus its graphic EQ versus the Mark V's 2C plus mode on channel 3 with its graphic EQ as well. So the graphic EQs are contributing to the tone, which kind of makes it really difficult to dial in and nail the exact tone between the two. So you can hear some slight differences, but for the most part, they're really on par with one another. Let me flip that switch back and forth so that you can hear the plug-in versus the real amp, and see if you can tell me which version is which. So we're going to start with A. We'll switch to B. Back to A. B. I'm going to kind of randomly flip back and forth, and you tell me what you think is what. Pretty close. So anyway, you can do a lot of cool things in here. For example, we have all 5 of the graphic EQ sliders here. In case you didn't know, they are resistor, inductor, capacitor, an RLC circuit, and we can tune all of the values here. So we can drop this guy down to a 470, and we get a little bit of a wider bell on the 750 slider. more resistance is a narrower bell, whereas a lower resistance is a much wider bell. And you'll see some variation in the graphic EQ circuits out there, and some of them have this middle slider at 1K, and some of them have it at 470. So I like it at 1K, but its default is 470. That is what the original 2C Plus had, I believe. We can also, of course, tune the center frequency. So that's pretty wild. Obviously, this is the most impactful slider on the EQ, as well as the 240. I like these really far down low. And if I had a picture of the graphic EQ on the Mark V, you could see it's just about exactly this configuration. There's a little bit of difference in the tapering of these sliders. This is using an S-curve taper, and you can vary a parameter that says how S-y it is, for lack of a better term. So you get a lot more sensitivity in the middle of the range rather than on the edges. So it just depends how you tweak those values, and that's kind of the behavior you get out of it. This is kind of a pretty cool approach because I haven't done that much hard coding within the plugin to be specific to the 2C Plus. I have actually expressed the circuit in the source code itself. So I could change the topology of the circuit kind of at a whim. I could add a resistor in here, or add a capacitor in here, or, put a capacitor in here in parallel. It's just a simple change at the code level. And then what happens is the C++ compiler is really doing a lot of heavy lifting here and optimizing the stuff that actually simulates the circuit. So it has all the knowledge of all the components, and it can run compile time algorithms to simplify the code or optimize the code to simulate this circuit. And we can do this, again, for any circuit. So I've been looking at like dual rectifier circuits. I could do Marshall circuits. I could do Fender circuits. It doesn't make a difference to the code. It's just a network of resistors and capacitors and tubes at the end of the day, and some switches, of course. So all of these things are a fair game. I just chose the 2C Plus because personally I love it. So it's kind of the peak of tone, in my opinion. I mean, maybe the user experience is not the best in the world with you having to use the graphic EQ to do everything, all the heavy lifting, whereas more modern amps, they have all of their EQ sections coming after the distortion rather than here where they come before the distortion, as you can see in the circuit. So the guitar input comes in here, goes straight into a tube, and we can actually look at what it does. If I reset my view. So this new color up here is actually what the guitar signal is being amplified up to, coming out of the plate of the first tube stage. And then from there, once you run it through a simple filter network, everything comes down to the 0 level. So it's got this 300-ish volt DC offset up here. You just run it through any capacitor of any kind, and that'll pretty much drop it down to the 0 volt. So it'll remove that DC offset. And then what you got to do, feeding the grid of the next tube stage, is to have a very low level. So let me go turn that output off. Anyway, if we come in here and we see how low this signal is, it's within the 1 or 2 volt range, and that's kind of what a tube likes to see. When a tube sees a more negative voltage, it lets that go through, but if it goes positive, it starts to clip that. So we can take a look at the output of this tube, and we can see what happens if we reset our view. Yeah, it boosts it way above the 300 volt with that DC offset coming off of it. And then, of course, if we take a look right after the capacitor here, that removes the DC offset. So we can kind of see what that's doing. That's significantly more volume, than what was coming out of the first stage. So there is some amplification, there is some clipping going on in these first two tube stages. And the volume 1 knob right here basically determines how much gain is going into the second tube stage. So that determines pretty much what the first stage of clipping is doing. And of course, we can play with the resistor that feeds the plate, and that can change the DC offset. So we can take a look at this. Oops. Sorry. Let me show you that. Yep. So our lower resistance brings it closer to our reference voltage, which in this case is 500 volts. And then more resistance brings the DC offset down. So it changes the amount of realistic output that you're going to get, the amount of variance from the reference voltage. So you just kind of want to have like a little sweet spot, and the original amplifier designers have found those sweet spots for you already. So all the default values within this circuit obviously are going to sound great, just like the original thing. But you can tweak and tune and, you know, just change everything to your heart's content, which is really fun. And I don't think you're going to find that in any sort of existing modeler out there. I mean, the fractal audio stuff, that stuff's fantastic. They have a lot of parameters in there. If you're into that, and if you want to get in there and tweak and tune everything, you can change, you know, the frequencies of this and that and the other thing. And they're not going to get down to the resistor capacitor level like we do here, but the effect is kind of similar. Like they'll let you tweak this brightness capacitor value, for instance. I know I've seen that in there. 180 picofarads, you can change that to 120 or 90 or 80, whatever you want, 300, 400. I know I've definitely played with that value, so you can definitely do that. I may want to create like a 2C++ mod for this. So we'll have a few more extra switches in here that engage some extra component paths that represent that 2C++ mod. If we're into that, I don't know, we'll see. Maybe that's a version 2 thing. So that's really all I got for you. It's been a blast doing all this stuff, and I hope you like it. Thanks.